It's a great pleasure to be here. Especially, I'd like to thank the organizers for giving me the opportunity to, speak on this very nice conference. A beautiful place. And today I'm going to talk about kind of a random dynamical system, so to say. So this fits into the title of the conference, and as such, there will be probabilistic techniques. But there is also going to be some amount of deterministic dynamics. And everything that I will say is joint work with Lai-Sang Yang from NYU. So let's get into it. There is a little bit of plan. So I will give you some introduction on the problem. This is actually a pretty classical problem. Another title could have been a fresh look at a classical problem. And then I'll discuss mean field limit for uniformly growing substances, mean field limit after depletion, and a little bit about fluctuations. You'll understand after the introduction what these words mean. So let's go to the introduction. And we are studying what we call a reaction network. So the motivation is coming from biology. In biology, there are a lot of complicated networks where various substances, through some chemical reaction, form new substances. And some of these systems sometimes are modeled by stochastic reaction networks. So here is the setup. You have n substances, and their mass is going to be denoted by x1 to xn, and these are time-varying quantities. And they interact with one another through k reactions. So each reaction, lowercase k, is going to update the amount of quantity of each substance possibly. So the change in substance n is denoted by a sub kn. So it is possible that a sub kn is negative. In this case, we're going to say that substance n is upstream for reaction k. Upstream meaning that reaction k is taking substance n as an input, does something with it, and produces perhaps another substance. So if AKN is positive, then through this reaction, this substance being produced, so you say it is a downstream, and it's quite possible that AKN is 0. I would expect if it is a large system with many substances, then most of the AKNs are zeros. That just means that the given substance does not take part of reaction K. Okay. So it's important to stress that I do not assume that the total mass is preserved. There is no reason to assume that. One possibility would be that you have injection of a substance from the environment to the system, or leakage, right? So if substances are leaking out of the system, then that would be a reaction which only has negative AKs. Okay, perhaps a few substances are upstream or downstream, and that's just an important assumption. Obviously, substances cannot go negative, so all these numbers are non-negative. And when do the reactions take place? Well, they take place at random times. So simplest possible model would be a Markov jump process. Okay, so the time at which it takes place, the reaction is a random time, and it's just a Markovian thing. Okay, so one special case, which is an important special case and is studied quite a lot in the literature, is called scalable. So I want to kind of scale the system, let volume go to infinity in order to make mathematical statements. And a convenient assumption is the scalability. So when you think about Markov models, there is always rate, right? So the rate function, which I'm going to denote by r sub k, so lowercase k is the index of the reaction, r sub k is the rate of this reaction, is sufficiently smooth, let's say C2, to avoid any degeneracies. It doesn't have to be C2 for all the results, but don't worry about it. And so the scalability is this condition, right? So if you multiply, so x is a vector and c is a scalar. So if you multiply a vector by a scalar, then the reaction function is going to be multiplied by the scalar. For non-negative, I don't worry about negative, right? Because all these x's are non-negative. So I'm never going to multiply by -1. There's no point. And obviously, the simplest possible scalable function is linear. right? So even for linear, there is interesting question. You might think that linear is completely obvious, which to some extent is true, but still, if you ask the right questions, still there are interesting questions. Okay, so that's pretty much the setup. So I'm going to be a little bit more precise. So I fixed capital N, capital K, number of substances, number of reactions. AK is the vector of the updates, and I collect them into a matrix capital A, and then the reaction network is defined as a Markov process, continuous time Markov process, with this generator, and the generator is just sum over all the reactions, and as you can see, it updates the state by adding this vector AK, and the reaction can take place if the new state is still non-negative. That's a very important assumption. This prohibits me from going into negative in any of the coordinates. And there is this rate function, which I still need to specify. The only thing I assumed so far is that the rate function is scalable. Okay, so this is the generator. And let me stress out the special case of the linear. So a linear function. So this is a linear function, right? So this would be a linear function of. So RK would be linear function of the xn's, and if you want to study linear reaction networks, then is a kind of obvious observation that you can get rid of this sum, okay, because you can write the linear combination as n separate reactions, and each reaction would be just fueled by one of the xi's, okay, because there would be a double sum, so you regard them as separate reactions, and in that case, we kind of like to use that point of view, because the reaction would be just a constant depending on k times x of one of the x's, which I denote by ek, and E stands for enzyme. That's kind of a biological point of view, that you have reactions fueled by enzymes. So each reaction has an enzyme which is driving it, and that's denoted by E sub k. That's always true for linear. All right. So this is the definition, and here is a specific example. You have, let's see, 2 substances, 4 reactions, and all the alphas are 1s, and the enzymes, this is a linear example, so the first reaction has enzyme 1, and all the other reactions has enzyme 2, so you got 4 reactions. This reaction is fueled by enzyme 1, and these 3 reactions are fueled by enzyme 2. And if you do a bit of simulation, then what you're going to find is pictures like this, that, for example, this simulation then corresponds for initial condition. The blue curve, okay, so there's a couple of things here. So the blue curve starts from here, and then it goes like that. And this initial condition is like 3,000 and 5.7 thousand, and then you get a trajectory like this. And for the orange, you start from 3,000, 7,000, then you get a trajectory like this. Okay, and this goes for a specific time t equals 0.55 for this particular reaction network. And if you do a similar picture for, instead of 1,000, you go to 10,000, then what you see is that you have very similar curves, except that they are much smoother, right? So, of course, it is not surprising that you do have a limit as this number goes to infinity, and then it is rescaled, right? So I rescale these figures, so it's kind of a scaling limit. And in the limit, you see something like a smooth curve, a very nice smooth curve here, very nice smooth curve here, until you hit the boundary, and when you hit the boundary, then something else has to happen, of course, because you cannot go to negative, so okay, you're kind of confined to the positive or non-negative part. Okay, so whenever you look at such a picture, I think there is a couple of questions that you can ask, and these are the questions that I do want to study here. So the first question, which is actually classical and everybody knows it, but I'm going to tell you anyways because I mean everybody knows who is working on this area, but maybe not everybody knows in the audience. But this has been known for a while, so there's nothing new in question 1. Question 1 is finite time limit. Do you actually see this smooth curve in the limit as you scale? And if so, what is the smooth curve? That's the first question. The classical one has been known for 50 years. And an immediate follow-up question is about fluctuations. So if you can prove that these converge to a hyperbola as you suspect, then what is the deviation between the hyperbola and the actual stochastic curve? You blow it up, and then because it goes to zero, obviously the difference, so you multiply it by a number that goes to infinity, and then you ask what is that stochastic process, right? So that would be fluctuations. So this is classical question 1. And now let's say you solved question 1, or you or you read the literature. Then there is question 2, which is doing the same thing in infinite time. There are some results for question 2 in the literature, but much fewer than question 1. So question 1 is completely understood. In question 2, there are some new questions. There are some examples that are not studied by the literature. So that you can say some new results for question 2. And question 3, at least in this community of people working on such problems, apparently has not been studied, or at least I'm not aware of any results on depletion. So usually, a very common assumption that people make in this area is that they assume that you never deplete, right? But if you do deplete, then you can still ask the same questions. Can you approximate the solution by a smooth curve on a lower dimensional manifold on the boundary of the orthant? And if so, what is the fluctuation, and so on and so forth. So let's say this is increasing order of difficulty, these questions. And so I want to, yes, question. Yeah, depletion means essentially this picture, that one of the substances goes to zero or close to zero, not necessarily exactly zero, but this picture. I have to give an exact definition, and I have to explore this area, but that's what I want to understand, right, in depletion. All right, so let's get into it. So I'm going to tell you the answer to question 1. It is pretty classical, and the answer to question 1 is yes. there is a smooth curve which is given by ODE, and this ODE is very easy to find if you think about it for a few minutes. And well, here is the answer. So the ODE is given by this this kind of infinitesimal growth. So if you are at x, then you define this infinitesimal growth, which is the weighted average of these AKs that take you to the next place, and you get this function capital F. Like you can think about it as an infinitesimal growth, and then you have an ODE. And then there is a result by, let's say, Kurtz. Maybe there is earlier results, but this is pretty early results. So maybe other people knew it before, but it's like already 50 years old, which is saying that if you pick a curve which stays positive, it is imperative that you have to stay positive, right? So you pick a curve of this, you pick a solution of this ODE which stays positive. So the positive orthant is denoted by O+. Then what you do is that the solution of the Markov process rescaled by L is going to converge to this path as you scale back. So L is very large. Initial condition is L distance away, and then you scale back by L. You converge to this solution, right? So this is this is the result. And let me just remind you that the special case which we kind of looked at is the linear case, when in case of linear, if all these reactions are linear, then of course right-hand side is linear, is going to be just given by multiplication by a matrix B, and this B you can define as, you can think about the entries of the B as the infinitesimal growth of substance M induced by a unit of substance, and when induced means as an enzyme. So all the substances could be enzymes, and when they are regarded as enzymes, then they kind of make other substances grow, or growth could be negative. So these entries of the matrix can very much be negative. So in this example, so this example, it would be hyperbolic matrix with these two eigendirections, and this eigendirection is the stable eigendirection. So it serves as a separatrix, right? So if you start on this side if you start on this side, then you go to this unstable eigendirection, and you grow exponentially fast, like shoo. And if you start on the other side, you want to do the same thing, but problem is you go hit the boundary, and you are not allowed to do that. Okay. So that is clear. Okay, so now question is, can you extend the result to infinite time? And some results that I am aware of in the literature is special cases. So, okay, important to note that if all these AKs are positive, or perhaps you have -1 on the diagonal, then this reduces to what is called a multi-type branching process. You know, in branching processes in probability theory, there is an individual who dies and then produces offsprings. In multi-type branching processes, like a type, the individuals have finitely many types, and when they die, they produce offsprings, perhaps of the other types. And that's exactly what has been studied a lot. And in this example, oftentimes you have a pair of Frobenius kind of picture. Well, if all the entries of the matrix are positive, then you have a pair of Frobenius. If they are not all positive, then some degeneracies. But essentially, as long as you have a pair of Frobenius kind of picture, then you don't have to worry about depletion, right? If all the entries of the matrix are positive, you don't have to, depletion can literally never happen. So classical reference goes back to this book by Altreja, Ney, and more recent work, Jansson, who kind of explored the entire linear algebra picture. So he has this pair of Frobenius kind of matrix, and then projects it to lower eigenspaces. Not the leading eigenspace is very clear. You go to infinity with exponential speed, but he also projects it to lower eigenspaces and studies complete picture. But always, he always has a non-depletion explicitly because of the construction of the model. And some other class of results is first of all, I apologize if I miss some references. But some results that I'm aware of is Pimantle, starting from the 90s, from his PhD thesis, I think late 80s. And he also has a nice survey paper from 2007, where he studies such problems. And Ben Naim is another reference. So some results could be said as Hartmann-Grobman kind of results near hyperbolic fixed points of the rescaled flow. So whenever you have a scalability property, then you can always project the ODE to the unit sphere, right? So this is the projected solution to the unit sphere. And if you have like a hyperbolic fixed point, then there are many results saying that if it is a sink, you can converge it. If it has unstable eigendirections, then you can not converge to it with the stochastic process, stuff like that. But what I'm not aware of is like a general theory for bigger class of reaction networks. And what is funny, even for all linear reaction networks, I'm not aware of results. So if you consider all matrices and perhaps all or almost all solutions, maybe ruling out some degeneracies, then as far as I understand, they don't cover all those cases because you don't necessarily have a Hartmann-Grobman kind of hyperbolic fixed point. Okay, so what are the possible limits? This is a question, and this is a question that I want to answer now. So let me focus on the linear case. So let me here just repeat what I said before, that this is a linear ODE, and phi t is the projection to the unit sphere of this solution. And well, what is omega limit set? The omega limit set is, well, this is what it is, right? So I guess people know this is a dynamics conference. But so omega limit set means that you have a subsequence along which you converge to that. And I want to define it on the projection because normally the example that I want to look at is the solutions diverging to infinity. So that doesn't really have an omega limit set, or infinity is the omega limit set, but that's not what I want to look at. So I project back to the unit sphere, and then I define the omega limit set, right? So whenever I write phi, lowercase phi, that's the projection on the unit sphere, and x's are on Rn. And the omega limit set of x is just defined as the omega limit set of the projected thing, because I don't want to worry about going to infinity, but I do want to go to infinity, right? Okay. So that is the definition of omega limit set. And I'm going to say that the projected solution as well as the thing. So let me maybe just draw this. So you have some point here, and then maybe ODE goes to infinity, and then you project it back. So this would be x naught, this would be phi naught, and this is phi of t. And you say that it is omega stable if for any open neighborhood of the omega set, there is some delta, such that if you perturb initial condition by delta, then the omega limit set is going to be contained in this neighborhood. So it's like stable for perturbations. Okay, so here is a simple proposition which you can discuss in your undergraduate ODE class if you have good students, that for any n by n matrix, there is a subspace of dimension strictly less than n, which is like exceptional subspace, such that if you are not in this exceptional subspace, like this one would be exceptional subspace. No, sorry, not this one. The one which is the separatrix. So if, like the other one. So yeah, this picture is not consistent with the one that I had on the, because, yeah, anyways. So let's say this is unstable direction, this is stable direction, and then you have a solution like this. Then obviously this subspace is problematic, right? Because here you will not have stability. So you have to rule out this subspace, and for everything else, you always have the following three possibilities: that the omega limit set is either a fixed point, a circle on which the dynamics is periodic, or a d-dimensional torus on which the dynamics are quasi-periodic. So here you have fixed point, right? And how can you get periodic or quasi-periodic? Well, you can get that if you have some resonances, I guess. So if this is spectrum, and then eigenvalue with highest real part would be, let's say, lambda. And if you have some other pairs of complex conjugate eigenvalues, let's say lambda 1 and lambda 1 conjugate, and maybe more, then what you're going to have is that you have solutions that go to infinity at exponential speed, but also spiral out. And what you have to look at is this set of real numbers, which is imaginary part of lambda, where real part of lambda is equal to lambda 1. This is a set of real numbers, finite set of real numbers, and you look at you look at if you consider Q, so this is a set, I don't know, S, and then you consider QS. Then you look at the number of maximum number of linearly independent set over Q, right? And that is going to be dimension of the torus. So, for example, if you have two pairs of complex conjugate and they have linearly dependent imaginary part, then it means that you go around, let's say, 5 times in this two-dimensional plane, and at the same time you go around 7 times in the other two-dimensional plane. So you're going to have a circle, right? A circle which is winding around in the 4-dimensional space. But if they are irrational, if they are not rationally related, then you have a 2-dimensional torus embedded into 4-dimensional torus. So you're going to have this third case, right? It's just Kronecker theorem, like a linear flow on toruses. Okay, so and just one last definition, that a solution point is traceable if solution stays in the interior of the orthant forever, and omega stable if omega limit set is also in the interior. Because I again want to rule out some degeneracies, right? I don't want omega limit set to be exactly on the boundary, because then I have to worry about whether I cross the boundary or not. So under these conditions, which is typically like this is so this result holds for almost every initial point, and this is condition on the solution of the ODE. If it doesn't hold, then of course you cannot trace forever. So under these kind of minimal assumptions, we can have infinite tracing, right? So this is the same result as Kurz, except t goes to infinity, right? So there is it's not a finite time result. You can approximate solution forever under these assumptions. So first assumption is that you need to have exponential growth. Of course you don't. So the leading eigenvalue, like this picture that I drew, so this real part has to be positive. And what else? And x naught needs to be traceable. So the traceable means that it is omega stable, and the omega limit set is not on the boundary, because if it is on the boundary, I have to worry a bit about whether I cross the boundary or not, and I don't want to worry about that, okay? So this is basically for all matrices and almost every initial conditions, we can tell if there is depletion in finite time, or if not, then we can go on forever. Okay, so this is first result. And the corollary is that omega limit set of the stochastic process, which is a capital omega, so it's a random set, as a consequence with high so these statements hold with high probability, right? So if you read the quantifiers for every epsilon and delta, there exists L0, such that for every L bigger than L0, and with such initial conditions, the following holds with probability 1 minus delta. Because there is always a little chance that it doesn't hold, right? So even if I want to follow the ODEs, this is a stochastic process, so it might not. It might cross the separatrix. If it does cross the separatrix, then it will not satisfy this. So you have to discard event of small probability, and with high probability, you know, probability 1 minus delta, your omega limit set is either a non-random point or a random point or a random torus. So non-random point means that a point which a point which is not random, or deterministic, but non-random point is special case of random point, of course. Yeah, question?
Capital omega is the same as
well, capital omega is the same, except that it is a stochastic process, so not an ODE. Like usually lowercase letters stand for deterministic and capital letters stand for random. And you also, of course, know the growth rate. So the growth rate is exponential with this exponent e to the lambda 1. And there is polynomial correction, where the polynomial is just size of the biggest Jordan block, right? This is, again, like usual ODE, like usually solution of the ODE grows like this, right? There is a resonance. Okay, so maybe the proof is not very exciting. So anyways, it is just some probabilistic techniques. I wrote these 5 lines. So okay, so let me say these 5 lines. So we use Kurt's theorem to move trajectory close to the omega limit set, because for finite time you can use Kurt's theorem. And then you denote by tau first hitting of the wall, and then you use this process here, which is if you knew you don't hit the wall, then e to the minus bt times xt would be martingale, but it's not quite correct, because you might hit the wall, so you don't want to go beyond hitting the wall, so you just take minimum of t and tau. So this is vector valued martingale, and then use tools from martingale theory, like martingale convergence theorem or Dub's inequality in separate eigenspaces, and then you get this result. Okay, so maybe I will go on to what happens after depletion. So what happens after depletion? So let me see. I need to draw a bit of a picture. So I guess that maybe easiest or simplest non-trivial case would be 3 dimensions. So you pick one wall for simplicity. So you say you hit this wall. Okay, so you have an ODE which you just discussed, and let's say the solution of this ODE is such that you actually hit the wall, and then you want to ask yourself what is going to happen, right? So this is you have Rn. And now you have here Rn minus 1. And for simplicity of notation, I am assuming that this Rn plus 1 is such that xn is equal to 0. Yes? So you can see there xn is equal to 0. And now in this Rn minus 1, you also have O n minus 1 plus, which is orthant in n minus 1 dimensional space. And in this space, I'm going to consider another region. Let's say this region, which I'm going to denote. So this is Rn minus 1. And this region I'm going to denote by D. Okay, so what is D? So there is a definition of D on the board, on the slide. That is basically saying that such points where the ODE, let's say linear case for simplicity, okay? The ODE solution would cross the boundary transversally. So it is just saying that I want to rule out some degeneracies. So I already have vector field, right? Which I already defined by Kurtz. And this vector field needs to point strictly out. Okay? And this is the definition of D. So maybe vector field at other parts of the boundary is pointing inwards, or maybe somewhere else it is exactly in this n-1 dimensional space. So that's kind of the generis. So when I hit the wall, I want to hit it like straight, heads on. At least this coordinate is pointing out. Okay, so this is definition of D. And now we have this following theorem, that the theorem is saying that there is a local Lipschitz function which is denoted by calligraphic F, defined on D and takes values in Rn-1, so it's like a vector field, such that the following holds. If you fix initial condition in D and capital T such that the solution exists and this stays in D. So anyways, I promise that there is local Lipschitz in D. So I don't know what happens on the boundary. Maybe Lipschitz goes wrong, maybe the vector field is not defined, maybe something horrible happens. So I want to consider solutions that stay in the interior, right? So this is again finite. This is a finite chunk. So this is a solution which stays inside this domain D. And whenever I pick such curve, then I get the same result as before. That I scale, I go distance L is very large, and then I look at the first n-1 coordinates because I know the last coordinate is essentially 0. And I rescale them by L, then this solution will converge to deterministic solution, right? So this path will converge. So you start from L very far out, and sorry, maybe better to say you start from here. So basically, initial condition is saying that in first n-1 coordinates you start very far out, and last coordinate is tiny, big O1, and then you divide by L. And then the solution is going to converge to deterministic path given by this yt. Okay, so perhaps your question is what is this ODE? But maybe we have a question.
Wouldn't F be the reduced equation?
No, F is more complicated than just the reduced equation. So F, of course, is related to the original vector field, but in a more complicated way. So if I only tell you the original ODE, then you won't be able to find this F, because you need more information. So the original ODE is a mean field equation which you got from the stochastic reaction network by forgetting some amount of information. It's like looking at only the drift as opposed to looking at the entire stochastic data. And that coarser piece of information is not enough to find this F. You have to look more closely into the stochastic reaction network. Okay, so let me explain what is F. And at the same time, let me explain to you why this theorem holds. I won't give a proof, but I give you an explanation, and there are many experts here, so they will be able to reconstruct the proof. So the observation is you look at it as a fast low system. So the xn guy, the guy that is very little, you regard it as a fast variable, and then everybody else, which is large, of size L. When you rescale them by L, they become big O1, they would be slow variables. So the xn, the last coordinate, is not exactly 0, it's close to 0, but it could be 1, 2, 3, maybe 15, but like a finite number. And that changes more rapidly than the slow variables. That's why they are called slow variables, because they are of size L, approximately L. So when you rescale them by L, they change more slowly. So there's a separation of time scales here, a fast and a slow variable. And then you can use those tools from a study of fast low systems. So one thing is you can identify this right-hand side F with this kind of point of view in the following way, that you regard xn, which is the fast variable, on time scales that are faster. So these guys will change on the time scale L. So I'm looking at a time scale which is much less than L. I fix a t, and then I add s plus s over L, where s is much less than L. Then essentially the slow variables are fixed, and if I pretend that they are literally fixed, then the fast variable would become a Markov chain, a one-dimensional Markov chain. So on this picture, you'd have, well, I drew the domain for n-1, but I didn't draw the last coordinate, right? So that would be R, this coordinate, and then there is actually integer. So these can only take integer values. So you got n, which is natural numbers.
So
xn just becomes a random walk, except if you have sufficiently small when you practice certain jumps?
Yes, good observation. So what Guillaume said is that xn is essentially just random walk if the value is sufficiently high, and if it is low, then I don't allow jumps that would take me to negative. So it's okay. Even Markov chain is a little bit of a fancy word for this process because it is random walk upstairs, and when you get, let's say the smallest jump is -10, you can jump up to -10. Then starting from 10, you have random walk if you are at height 10 or higher. But if you are at height 0 to 9, then the jump -10 is prohibited, right? So this is your fast variable xn, and assume. Okay, so if you like this point of view as a random walk sufficiently high level, then you know that perhaps you want to assume this irreducibility assumption. So for simplicity, I'm assuming that this random walk can go everywhere, right? So the greatest common divisor is equal to 1 of the steps. It's not necessary to assume, but let's just assume for simplicity. And if you assume that, then there is going to be a unique invariant, which is necessarily ergodic measure of this Markov chain, right? Because you have a random walk high up, and the drift is negative, so you're always being pushed down. When you go down, then you have some other steps, but it doesn't matter because if you're high up, then you're always being pushed down. So that guarantees that you have invariant measure, but you want a unique one. I guess for simplicity, so I'm assuming that the greatest common divisor is 1. It doesn't really matter.
But
yes.
needs to be integer or not?
AKN is integer, yeah. So it could be rational, in which case I just multiply by the common denominator. And but I suppose that if they're very rational numbers, the picture would be different. So if there is, you can jump 1 and square root 2, then I believe the picture would be different. But I'm assuming for simplicity is always integer, which is the same thing as assuming they are always rational. Okay, so everyone agrees that it has uniquely ergodic invariant measure, which of course depends on the slow coordinates, right? So I'm going to denote it by mu of yt. Again, why does it depend on the slow coordinates? Because the slow coordinates serve as enzymes, and it does matter what is the quantity of enzyme, right? If one enzyme is twice as much as the other, then those reactions will go at double the rate as the reactions fueled by the other guy. So the probabilities of these jumps of this random walk do depend on the slow variable. The actual size of the jump doesn't depend on the slow variable. So you have a unique measure, which you denote by mu, is a measure on n non-negative integers. Okay, we are in France, so I have to tell you whether 0 is a natural number or not. I know it's different in France than in other countries, but I forgot which one is which. So anyways, 0 is allowed, okay?
But why do they stick to the integers?
Oh, because I assume that the jumps are irrational, so it's just the same thing as integer.
Why should xn just jump from integer to integer?
That was one of the assumptions, that the jumps are given by these numbers akn, and I assume that akn are irrational or integer. It's the same assumption. Okay, so if you agree with this invariant measure, then you just assume that the fast coordinate is already, the fast variable is already distributed, because it's very fast, so it's already distributed according to its unique invariant measure. And if you have this, then you can apply the ergodic theorem and compute the infinitesimal drift of the slow variable, right? So the slow variable is going to be, this is the infinitesimal drift, which depends on the slow variable as well as the measure, or the invariant measure in the fast variable. So this is what I denote by calligraphic F. You can actually, you can give formulas, but they are not going to be very explicit, because invariant measures of these Markov chains are usually not very explicit. So here is a few comments. So in order to turn this argument into a proof, you just have to fill in some epsilons and datas, right? So basically all is relatively standard, but let me highlight two steps. First is that you need to verify that calligraphic f is locally Lipschitz, otherwise the ODE might not be well defined. And for that, what you need is two things: that this Markov invariant measure is mixing and exponentially mixing, and the mixing rate is uniform, at least locally, which is like Harry's theorem. You can verify it by Harry's theorem, and then you also wanna see it is local Lipschitz. Actually, much more is true. You can have a linear response formula, which basically means C1, right? Because you have a parametric family of Markov chains, and you want to see if the invariant measure is smoothly dependent on that parameter. Lipschitz is enough, but C1 is what is basically usually discussed. So one particular paper that we looked at is Heirer, Maida. But in any case, so just wanted to say, like, of course, there are experts here on linear response, and people study much more sophisticated systems than just Markov chain. Maybe just a side remark that this is continuous time, and most of the work in linear response theory is on discrete time. But I'm not saying it's difficult, but if you just Google linear response, then usually you will find discrete time results, not so many continuous. And here it's maybe when you prove V convergence by we prove V convergence by martingale method is probably not necessary in this result, but I do want to a little bit in the last how many ever minutes I have left. I want to go to fluctuations, and in these fluctuations is a very natural tool to use martingale method. So if you insert these two little bullet points into this argument upstairs, then it turns into a rigorous proof. Okay. All right. So yeah, I guess I just spelled out. So this is the formula that you get for the right-hand side, but it's not particularly illuminating. And I think I wanted to make two quick remarks about it. So first remark is that actually this is going to be a scalable vector field. So even if you start with linear, you get scalable. I mean, this result you can prove for scalable, but I mean, just saying that even if you assume that the reactions are linear, which seems like a very serious restriction, then you get like a pretty ugly vector field after depletion. So even the linear assumption doesn't help much, so to say. And another remark, which I think I already implicitly said, that usually you cannot compute invariant measures explicitly. So this formula is kind of implicit. But well, one example when I can compute, or anybody can compute, if you can only make one step up, one step down. If you only make one step up, one step down, then you can explicitly compute the right-hand side. So it's like an explicit ODE. Okay. Usually it's difficult to compute, even if you have just random walk, where you are, when you restrict the guide to go to negative, then finding invariant measure is like not very explicit computation unless you have some very simple special case. Okay. Yeah. So I guess that's about the main main results, so to say. The main message is that you have a fast low system coming up, and maybe another thing I just wanted to real quick tell you, that if I go back to this picture, that so here this ODE is a one-dimensional ODE, is scalable. Scalable one-dimensional ODE has to be just multiplication by a scalar number. It's a one parametric family of ODEs, and it is just negative number. So you hit the wall, and then you start to decrease in this coordinate. It's not literally zero, but you can't see it on the. So here maybe you can see it's like wiggling a bit around zero. It's not literally zero, right? So you have this. You have the fast variable, which is big O1, but I scaled by L, right? So here this is 1,000. So maybe this is 10. So that's why you don't quite see it.
In dimension 2, does it need to be negative number necessarily?
No, in dimension 2. No. In any dimension, it doesn't have to be negative. Like it can be any number. So one thing I wanted to say, even in dimension 1, dimension 2 especially, that we can very easily turn this back. So one thing we can easily do, if you can, but throw in two more reactions one that goes up, one that goes down, and you make them in a way that one of them is tempered by the depletion, and that way we can make this guy turn up even if the mean field ODE in the interior is unchanged, even in one dimension, in two dimensions likewise. So this ODE after depletion is quite different from ODE before depletion. And obviously, one question is what happens when you deplete in another coordinate. So, well, I guess you can imagine that if you hit Rn minus 1, and then maybe it's like, okay, this picture is maybe not what you want, but let's say D is like this. So you hit Rn minus 1, and then you hit another roll again. Then you just have to do the same story again, that you drop the dimension by one more, and then you have a two-dimensional fast variable, which is a Markov chain on N2, and then you have again fast slow. So maybe not the most interesting. It's like basically the same phenomenon. And finally, you might hit 0, like in this picture, you actually hit 0, and then you can study what happens. So if you hit 0, there is a chance, depending on the combinatorics, there is a chance you literally hit 0, right? 0, 0, and then the reaction network is stopped forever. And there is a chance that you don't hit 0, you hang around here for a while, and then like the separatrix is here, comes back to 0. So you cross the separatrix, and then you shoot out to infinity. So there are other simulations which I didn't bring to you, that sometimes there is a positive chance that you hit literally 0, and then you shoot, and there is a positive chance you shoot out to infinity. So you can revive networks that died before that one way. And maybe just how much time? Maybe I have 3 minutes, I think. So I just want to say fluctuations. Yes. I don't think that, but I don't have a rigorous.
But it may be that there is something that is still there, but it cannot react with anything else because it's gone.
Yeah. So. Yeah. So I don't. So in this example that I brought up, I know what is happening, but in general, I don't have a theorem. So in this example that I brought up, what is going to happen? There is a positive chance you hit 0, but you can make that chance 0 by combinatorics. You can make the reaction network such that it always stays one coordinate is always an odd number, and then you can never go to 0. But that's kind of combinatorics, which not super realistic phenomenon in real biological systems, so to say. Okay, so just maybe 2 minutes about fluctuations. So, okay, where is fluctuations? So fluctuations are, next question, which people oftentimes study. Well, I guess like first question is finite, the mean field picture in finite time, and the next question people usually ask is either going to infinite time or zoom in for finite time, right? This kind of similar questions. And we already considered infinite time, so now let's consider zooming in. So if you zoom in, then what you're going to see, second order approximation is given by SDE. So it's also a result by Kurtz, 71 paper, is that in this kind of setup, as long as solution stays positive, then you're going to have SDE, where you have drift and what is it called, volatility. And drift, so basically you have already ODE solution, and then you linearize vector field along the ODE. This is going to give you drift term, and there is a variance or a standard deviation, which is given by a closer look at the local picture. So you have this infinitesimal variance, you take the square root, which is like positive, at least non-negative definite matrix, but we can assume for simplicity is positive definite matrix. So you have square root, and then it's again classical result. So basically what happens is that the curve really gets close to the ODE solution, but then you zoom in, multiply by square root L, then the deviation between ODE and the real curve is given by SDE, right? So it's like central limit theorem as opposed to law of large numbers. And so that's a Kurtz result, and we do the same thing, but we haven't really written it up. So there is like one preprint, which we already wrote up, is available on my website, and there is some work in progress where we do basically this. fluctuations is the same result, same kind of result, but formulas get a little bit more complicated, so I didn't bring any formulas, but basically the same style. So you have infinitesimal drift and infinitesimal variance. Infinitesimal variance is given by, again, you average a fast variable with respect to the unique invariant measure, and then you consider central limit theorem with respect to this measure. There is a Green-Kubo formula, so it's a little bit more complicated formula, but there is a limiting covariance matrix, and that covariance matrix shows up in the SDE as well as the infinitesimal drift. So
could you maybe show that instead is probably the same? An SDE with noise that is order 1 over square root of L, something like that. Instead of doing the limit rescaling, just saying that maybe you wrote it in the previous slide.
no, so I consider finite time thing. Square root of L. So square root of L is here.
Yeah, no, but go back.
Yes.
Okay, because that is the variance, yes. But if you write dx should be maybe f plus 1 over square root of L times some random noise. Something like, that should be essentially the same equation.
So you talk about, when you say the same, meaning that this as this and this, so the ortant and the depletion case. That's what you meant? Yeah, it is essentially the same. I agree. It is essentially the same equation, but the formula is more complicated because you have Green-Kubo formula as opposed to explicit matrix. But yeah. Okay, I think my time is up. So thank you.